So Kim, you'll be talking about federated learning architecture for Open RAN, and very soon I'll be introducing you, but this is the last talk. After that, we'll spend maybe 20 minutes or so going over the talks, and I took some points, some next steps for each of the, okay, I think we're back. For each of the discussion we had, and then we're going to follow up with each of you. So Dr. Kim Khoa is an associate professor in the Department of Electrical Engineering and founder of the IoT and Cloud Computing Laboratory at the University of Quebec's Ecole Technologie in Montreal. He holds a VMware industrial chair in multi-cloud service, grid, and edge AI. In the past, he served as the CTO of Technologies. Now is country in Canada. World's leading companies in software-defined network SDN solutions. He's also leading R&D large-scale projects with VMware, Ericsson, and Ciena, TELUS, Interdigital, and Ultra Electronics. He's the recipient of Microsoft Azure Global IoT Contest Award in 2017 and Ciena's Aspirational Prize 2018. He's author of 175 publications and holds several industrial patents. His expertise includes network optimization, cloud computing, IoT, 5G, machine learning AI, smart city, high-speed networks, and green ICT. That's great. You cover all aspects of what we're trying to look into. It'll be an interesting talk to see how we put those together. Thank you. You got about 20 minutes plus 5 minutes Q&A. Thanks.
Okay. So thank you very much, Dr. Tuta, for your presentation. So this is the last presentation of this session. Hopefully, it's not least, of course. So my talk will be about the federated learning architecture for Open RAN. So in this talk, I'm going, to explain the necessity of having federated learning architecture for Open RAN. Why we are using federated learning instead of, a traditional one. And why do you need, standard? And I will also present some use cases and a demonstration that we've done before, for partners as well. So this work has been done in collaboration with VMware Broadcom, in which I'm holding the chair. So first, why federated learning for ORAN? So first, ORAN is designed for with a native AI support. You already, see in the previous presentation. I'm not going, to say it again. Here, you can see in this figure there is a comparison between the regular or traditional machine learning, called centralized machine learning, and federated learning. The difference here is that you can see here. If you are doing centralized learning, that means all the devices have to send the data. To the central, components, elements, and in which the machine learning model will be trained. In federated learning, each device can train a local model by itself. With a small data set, perhaps. And then instead of sending the raw data, it will send the parameters of the models only. To the centralized entity, which is called aggregator. In which the machine learning model will be built, and then the global model will be sent back to all the devices. So this way will help to protect the data privacy. Because you are not going to send the raw data to the central unit. And also, it can take advantages of the processing capacity of all the devices, which is very, very appropriate for the telecommunication network operator architecture in general. Because you see, in the telecommunication network, by nature, it's distributed, and there are many, many elements. So if you send all the data to a central unit, so like in the internet now, so it consumes lots of network resources. And we cannot take advantages of the local processing capacity. Okay, but however, okay, training AI model, okay, here in Oran, okay, face challenges. Okay, I just want to add, let's say, some other arguments here is that, okay, Oran architecture is disaggregated. Okay, so distributed training is better than centralized one by nature. Okay. The second argument here is that, okay, unlike the internet-based application, okay, which is basically best effort, okay, telco application require the greater services. That means you can not only train, but have to train with the quality services. And the model that is built, it should be returned with the quality services. Okay, quality services here is not, let's say, in terms of, let's say, jitter delay gig traditionally, but the accuracy of model, the latency to train the models, and the action that will be made by the models itself. Okay. And then, okay, telco user pays their subscription for being protected by privacy and security. So we cannot share, telco operator cannot share the data of the users. Okay. And other things that, okay, related to 5G, okay, and 6G, okay, we have URLC, okay, and other, let's say, even lower latency services, okay, that requires the model to be trained very fast in parallel, okay, and to update continuously. That is, let's say, very, very, let's say, critical, okay. So as you can see, you get through the, let's say, existing applications, most of AI application for RAN, or all of them, okay, are trained centrally, and we want to change it, okay, and moreover, okay, we want to optimize RAN resources for training AI model. Okay, so we want to propose standards, to do it, to increase interoperability between the federated learning models and telco operators and vendors and AI developers. So this, we have, let's say, a very solid theoretical framework of this. We have, let's say, many publications for learning for RAN. Okay. One of the latest publication, for example, have been published in IEEE ACM transaction networking, one of the top in the area. Okay, so if you want, you can read it. Okay, I'm not going to present in details. Okay, that's one to see that we develop both. Okay, mathematical model, to guarantee the quality of the model, our architectures, and also implement it in reality, okay, through our collaboration with industry partners. Okay, some of features of our architecture could be, for example, you can train the high accuracy AI model using federated learning without sending raw or sensitive data through the network. Okay, our model can be very scalable because you can train in parallel. Okay, it can preserve privacy. Okay, and it is resource efficient and time efficiency. Okay. So it can also optimize for ORAN architecture. Okay, for example, okay, it can collect data in real time from the ORU, for example, Gnode B, okay, or ODU, okay, or tenants, and train model locally, okay, with privacy and resource constraint through the standard interface of ORANs, okay, and then, okay, we send the model to the central rig, for example, okay, to aggregate the model, and then improve accuracy. Okay, and our architecture will leverage on ORAN rig interface to synchronize between local and global models in real time. Okay, and in particular, okay, resources is also optimized for model training. As you can see, okay, in the federated learning, we can have, let's say, trade-off between the local computing capacity and the communication resources. Okay, so basically, it's an optimization problem. In some cases, when we increase communication, we can offset some of lacking computing resources. And it is very, very, let's say, great advantages. Okay, and in addition to this, you can see that, okay, if you use this kind of AI training, okay, the AI model can be deployed immediately, okay, and continuously onto ORAN elements because the training will be fully integrated with ORAN architecture. Okay. So here's sample use case that you can have with the ORAN architecture, okay, implemented with federated learning is that, for example, you can optimize MNO, okay, mobile net operator infrastructure for supporting multiple mobile virtual net operators. Okay, you can see that is, let's say, very, let's say, high wanted model at this moment. Okay, now someone, okay, an MNO, okay, have a large physical infrastructure, and the structure will be shared by multiple MVNOs. Okay, so MVNOs will, let's say, send the models instead of the data, to help the MNO to optimize infrastructures. And in turns, okay, the MNOs, let's say, can send the model, okay, to the MNO, okay, without, let's say, revealing the real data of the infrastructures. Okay, the sovereignty management is another, let's say, interesting use case. Okay, in which the MNO network can be managed using AI. Okay, with sovereignty, for example, some data can be sent within a country only. Okay, here's the case between the US and Canada. And you are working with some telco operator, and say, okay, in this case, if you want to, let's say, to optimize the routing, we have to send across the border because of the, let's say, okay, the overlapping, okay, in the territories. Okay, but okay, it's not allowed. Okay, so in that case, instead of, let's say, sending data or sending, let's say, routing information, we send the model. Okay, parameters only. Some other use case, for example, okay, distributed RAN optimization, okay, in which you can optimize both, okay, intra and inter-RAN traffic steering, okay, without sending data, okay, raw data. This is also interesting. Okay, energy efficiency both for local and global levels. Okay, or you can use anomaly detection with short and long-term correlation. Okay, it's also very interesting, let's say, use case with federated learning. Okay, and at the application level, you can use federated learning, to build the models for fleet and vehicle management, robot swarm control, many types of, let's say, distributed application using AI. Okay. So why do you need, let's say, standard, okay, for this? Okay, so first of all, okay, we can see the new regulation on AI. Okay, in particular with respect to the privacy. Okay, so if you remember last year, you have, like, say, Facebook scandal. Okay, on this. Okay, and telco operators are much more sensitive to regulation than internet-based company. So free learning is the way to preserve privacy. Okay, the telco operators prefer, let's say, to keep data privacy. Okay, but they also want to exploit this one. And telco operator does not have, let's say, large team on AI. Okay, so okay, if you can have, let's say, standards, we can connect the AI developers with telco operators. So AI developer can exploit the available data of telco operators. Okay, and in turn, okay, the telco operators can enrich their portfolios with new AI applications, okay, which is, let's say, the trend today. Okay, so a new standard, okay, we learned about interoperability between AI developers, telco operators, okay, both MNO and MVNOs and equipment vendors. Here I give, let's say, an example. Okay, for example, if a vendor designs a new hardware accelerator, okay, for ML training, okay, and the AI developers can take advantage of this accelerator through the standard interfaces provided by ORAN, okay, for free learning. Okay. Transparency, worthy, okay, trustworthy also can also improve. Okay, we don't know, let's just say it again. Okay, we can also optimize resource allocated for ML process through the standards. Without the standards, you cannot, let's say, you cannot optimize it easily. Okay, but if it's let's say, standard interfaces, okay, and the aggregation algorithm is standards also, okay, and the standard measurement mechanism, okay, for FL, okay. So in that case, okay, we can optimize. For example, we can exchange communication resources with the computing resources, okay. And finally, okay, in alignment with the previous presentation, we can minimize the social and environmental impact with this, okay. For example, energy efficiency can be much improved with this one. You can also, let's say, the substandards, okay, or guideline practice in order, let's say, to achieve energy efficiency for federated learning, okay, through the standards, okay. So here, that's a proof of concept that we already implemented, and we've done demonstration. I can share the video view. Okay, so as we are working with VMware. Okay, so in which, for example, here we are using a simulator to for the demonstration. However, okay, we connect also with some of the real equipments. Okay. So here in this proof of concept, we can have, let's say, multiple MVNO, okay, and we have an MNO, okay. The MVNO, okay, we send the models, okay, in order to help the MNO to optimize the physical infrastructures, okay. So that's his point. Okay. So here we can zoom in, okay, on the right side. You can see, for example, okay, here we have, let's say, the aggregator, okay, and the local channel, okay. So they're using the O1 services, okay, let's say to access it to the E2 node and get information, okay. And then, okay, the aggregator is running on the non-real-time rig, and the local channel is running on near real-time rig, or it can run also in the DU as well, okay. So this is a demonstration scenario that we've done before. Okay, we don't have much time, so I will, let's say, go very fast through this one. Okay, so the CRIG here of VMware is actually the non-real-time rig. Okay, here the local channel can run at the level of the edge. That means it can run on near real-time rig. Okay, as an XApp. Okay, or it can run on the DU as well. Okay. On the in the non-real-time rig, it's an ARP. Okay, we developed an ARP there. Okay, and our ARP can optimize the resources. Okay, in order, for example, to improve the learning time. Okay, or accuracy, or for example, with respect to the communications or computing resource constraints. Okay. So in this is, let's say, the demo setup, and we do the comparison between our Federated chaining and the traditional chaining, in which the model is trained centrally. Okay, some of, let's say, the figures that you can see here, okay, in terms of workload. Okay, here, if you are using, let's say, MN existing centralized MLN training solution, so you see, okay, the workload is always, let's say, almost, let's say, high. Okay, perhaps 100%, something like this. Okay, but if you are using, let's say, federated learning, okay, many periods here, we can save resources. Okay, so the resource consumption is much lower in using federated learning. Okay, here's for memory usages. Okay, we compare the aggregator with the central learning. Okay, so if it's in central learning, okay, it can zoom. Here we don't use much. Okay, only, let's say, 4 base stations. Okay, so the memory required is 5.6 gigabyte. And in the federated learning, you see only this order of 200 megabytes. So it's no, okay, it's great advantages. Okay, so like this. Okay, our demonstration will be, let's say, much detailed. So if you want to, I can share for you, let's say, through YouTube, okay, or I can send the link to you. Okay, thank you.
Okay, thank you, Kim. So Alex, Mehmet, you have any thoughts on this presentation? It appears you already have a proof of concept and several use cases that I'm very much interested to understand more. But Alex and Mehmet, please provide your comments.
Yeah, what I also see here is a vision for standardization. He outlines complete space, standardization space. That's excellent. I think it's probably more than one standard here. With the integration of AI, it's an interesting. We have now some project that Mehmet took. Mehmet can talk about it. Similar to AI integration, and but this is different. This is for ORAN. Yeah, this is excellent. I just like to mention something that not always we standardize regulations unless they're required to be standardized. Most of the time we provide mechanisms that enable regulation, support of regulations. So particularly for international standard that you make, where regulations change from country to country, you give them interfaces that allow them to. But sometimes we do, like masking, for example, the spectrum mask for unlicensed spectrum. That's in the United States. You're supposed to put it into the standard. Okay, Mehmet, do you have any?
Yeah. Yeah, it looks like it's ready to go, but I'm kind of interested if we write a project authorization request for this part, right? What would you say is the scope of this standard? Just very briefly, one sentence or two sentences. how would you write that one, or what would you say about the scope?
Okay. Okay, very good. Okay. Thank you, Mehmet. Yes, perhaps. Okay. For sure. Okay, it could be, let's say, kind of, let's say, very big, let's say,
Start
standard.
with the
Easy
word.
one. Yeah.
Start with the word. This standard specifies.
Yes.
Continue.
Yes, we want to define first the architecture, general architecture, okay, and then okay the interfaces, the main interfaces, and after that, okay, for example, we can have, let's say, standard for the federated learning sharing, okay, for the algorithm, etc. Okay, but we want, let's say, to define the general architecture, and then okay, each component will be developed over the time.
An architecture for what? For entire.
For learning for the setting, for example, okay. If you want to implement it like this, for example, the aggregator, where do you have, let's say, to put it in the ORAN, okay? If you put it in there, okay, which interface you have to use. So it can enable the interoperability. For example, here, okay, I'm developing a free learning model for my application. The others are developing another application, okay? So how we can, let's say, exchange the data, or how can exchange the model? Or for example, how if for example my aggregator can connect to the local channel of the other application, for example, without the standard architectures and interface, we cannot do it.
Okay, let me put words in your mouth. Let me say, and you tell me if I'm correctly understanding you. So this standard defined and functional ORAN architecture and interfaces. Yes or no?
It defines the federated learning
Okay.
implementation architecture in ORAN.
Excellent. So this is
federated architecture can work without ORAN, but how can we put it, let's say, in the most relevant way with ORAN? Okay.
Okay. So your subject is architecture is a federated learning. So this is the key. This is what you're standardizing.
Yes, for ORAN. Yeah.
Yeah, for ORAN. Yeah, it could be for something else. Yeah, for ORAN.
Yes, here is for ORAN. Yeah.
Right, but you're standardizing a standalone federated learning architecture. That's perfect. I mean, that's a very nice standard, I would say. Functionally sound, compact, and standalone, independent on other strings attached. You just do that federated learning architecture.
Yes.
That would be cool.
Yes, it kind of, let's say, reference architecture. Okay, it's like OSI, okay, something like this. But here it's for federated learning. Okay, OSI is very big, of course. But here, for example, if anyone want to implement a federated learning architecture for RAN, okay, we have a references model. We have standardized interfaces. We have the way to measure the performance, the learning time, guarantee the data privacy, etc. Okay.
Yeah. Well, this is very good because this is you're standardizing a capability.
Yes.
Basically, like we're doing now this like with massive MIMO. It doesn't exist. It cannot be a box, but it's a capability that can be standardized and then taken into any design that you do, like any modem. And so this is the same. This is like you're standardizing federated learning architecture, and then ORAN can use it. Somebody else will come up with some other generation of ORAN or something else, and they can use that too. I think this is excellent.
So, Kim, looks like you know what to do, right? Once if we start a project on this one, I think almost all of the content of project is in your mind, or you published a paper, right, on this.
Yes.
So you have 80–90% of the solution to this.
Yeah.
Okay. So I think it's a good one. I think we can start almost. I can think that we can start writing a PAR on this one.
Yeah, we'll be ready Monday.
We'll be ready on Monday, right?
For the next Monday, come on.
Did you apply for a patent or anything like that?
No, okay, we are not going to apply for patent for the architecture. Okay, no, it's not like this. Okay, but for example, okay, for the implementation platform specifically for some industrial partner, okay, but not for the architecture here.
I guess if you publish the paper, you can.
Yes, already. Yes.
Anyway, so
yeah, that's okay. You can have patents. It's okay. It doesn't matter. The only requirement that
what I'm trying to say is if you haven't patented yet, go ahead, do it right away. That's what I was going to say.
Okay.
Exactly. Yeah. Do it.
Mm.
There's nothing stopping you.
Okay. Okay. Thank you.
So that's great. I also, hello? Yeah, you can hear me, right?
Yeah.
So I also agree with your assessment. And only question to came, so this federated learning framework, can this be applied to something other than ORAN? Can it be more generalized? Or this is specifically customized to ORAN? I know you provided some use cases and your prototype is probably focused on ORAN only, right?
Mm. Yes, great question. Okay, in general, okay, federated learning can be applied for many other applications. Okay, but I think okay, it's particularly suitable for the telecommunication area due to the distributed, because it's distributed learning. Okay, unlike the centralized learning. But for the first standards, okay, for these standards, okay, we target Open RAN, okay, specifically. Okay, and for example, we define the model. Measurement models or implementation models, etc. Okay, for ORAN. I think okay for the first standard, okay, it would be enough. Okay, and then okay, depending on the support of the industry and other, let's say, partners, something like this, you can have, let's say, more standards. Okay.
Yeah, okay, excellent.
If it's,
Right.
if it's intertwined, if you're intertwining it, if you're integrating it, on the opposite approach would be if you create a standalone architecture, functional architecture, define generic interfaces in let's say 1955, and 1955.1 is for RAN adaptation. You could go like that, and then you would be open for others, forward compatible. So, but you need to think of modularizing the standard that will have different dynamics, because your architecture may survive longer than we will survive, right? But ORAN may not make it that, right? So will be something else, and the architecture may stay as a separate standard. So think of dynamics of pieces and separate if they have different dynamics and longevity.
Okay.
All right, thanks.